Hi, you can start now.
Hello, thank you everyone for coming. I'm Ted Weber. I'm an author, but also work as an ecologist and climate adaptation analyst. I have degrees in, a little bit about me, I have degrees in systems ecology and wetland ecology. I'm a certified forest ecologist and have worked on wildlife, habitat, and climate-related projects for over 20 years for the state of Maryland, the Conservation Fund, and Defenders of Wildlife. So first, I'll talk about the greenhouse effect and how it is increasing temperatures, melting glaciers, raising sea levels, and causing other negative effects. Then I'll talk about ways people can reduce the amount of future warming and damage and what can be done to adapt to the warming that's already occurring. Then finally, I'll try to answer any questions you might have. Please put your questions in the Q&A since I won't be able to monitor the chat. I am going to put my website in the chat, and the world is experiencing record temperatures and more severe heat waves. Canberra, the capital of Australia, set a new all-time high temperature record last year, 111 degrees Fahrenheit. 2019 was Europe's hottest summer on record, and lots of countries broke all-time records. So I don't have the information for 2020, and obviously summer 2021 hasn't happened yet. And temperatures reached 123 degrees in India. In Japan, a couple of years ago, 1,000 people died from the heat wave there, and more than 70,000 were taken to hospitals. And Miami recorded its hottest week ever last summer. Again, this summer is yet to come, but we're on track to beat that. Siberia experienced a period of unusually high temperatures last year, causing wide-scale impacts, including wildfires, loss of permafrost, and invasion of insect pests. The town of Verkhoyansk had temperatures above 100 degrees last summer, the highest temperature ever recorded above the Arctic Circle. So 100 degrees in the Arctic. In fact, 19 of the 20 hottest years ever measured with instruments have been since 2001. And the 5 hottest were the past 5 years. So this shows regional warming as of August 2020, based on global temperature records back to the 1880s. Most of the planet is either at its record warmest or much warmer than average. Well, so what's going on? Let's take a look at atmospheric physics. The energy from the sun comes into the earth in the form of light radiation that cuts through the atmosphere and warms the planet. The average solar radiation striking the top of the atmosphere is about 340 watts per square meter. 29% of that is reflected back into space, and 23% is absorbed by the atmosphere, and 48%, almost half, is absorbed by the Earth's surface. After the Earth absorbs its energy, some of the heat energy in the form of infrared radiation is radiated back to space. Carbon dioxide, along with water vapor, methane, and a number of other molecules, is a greenhouse gas. It lets in the ultraviolet and light energy from the sun, but traps some of the longer wavelength heat energy that radiates back from the surface of the Earth. Some trapping is actually good. It keeps the planet's surface warm enough for life. Otherwise it wouldn't be, otherwise it'll be too cold. But the problem is that we are thickening this greenhouse gas layer, and as it gets thicker, more of the outgoing infrared energy from the surface is trapped, which warms the planet beyond the levels at which ecosystems and human civilization are adapted. These graphs show atmospheric absorption and scattering at different wavelengths. The largest absorption band of carbon dioxide is similar to the thermal emission wavelengths from the ground, and it also partly closes the window of transparency of water, hence its major effect. This shows radiative forcing of different contributors to climate change in 2011, as reported in the 5th IPCC assessment report. The 6th assessment report, which I reviewed last year, should be coming out this year. Because it is the most abundant, CO2, carbon dioxide, is the largest driver of climate change, and it remains in the atmosphere for thousands of years. Methane only lasts about a decade in the atmosphere, but it absorbs molecule for molecule much more energy than CO2, and it's the second most significant greenhouse gas. Nitrous oxide, or N2O, also absorbs more energy than CO2 and per molecule for molecule, and it remains in the atmosphere for about 100 years. Then there's chlorofluorocarbons, or CFCs, hydrofluorocarbons, hydrochlorofluorocarbons, perfluorocarbons, and sulfur hexafluoride. These gases are sometimes called high global warming potential gases because each molecule traps thousands of times more heat than a CO2 molecule. So where does CO2 come from? For the most part, from respiration and combustion. Photosynthesis is the process where plants and certain microbes use chlorophyll or other molecules to combine CO2 and water to produce glucose needed for maintenance and growth. Respiration is the opposite process, using oxygen to break down organic molecules into CO2 and water to produce energy. Burning oil, coal, or natural gas is like respiration, producing energy from long buried organic molecules and releasing CO2 into the atmosphere. Using ice cores, scientists have been able to track CO2 concentrations over the past 400,000 years. As you'll see from the graphs, temperatures follow CO2 concentrations almost exactly and have caused changes big enough to start and end ice ages. Over the past 400,000 years, carbon dioxide levels have fluctuated between about 180 and 290 parts per million. But that's changed recently since the industrial era. 2019 averaged 411 parts per million, the highest concentration in 14 million years. And last summer, we reached 417 parts per million, so it continues to climb rapidly. As you can see here, CO2, nitrous oxide, methane, and sulfur dioxide concentrations have all been increasing dramatically in the past 100 years. This shows the same phenomenon compared to the past 20,000 years. And you can see that there is a massive uptick of greenhouse gases far above natural levels. The data show a very high correlation between surface temperatures and greenhouse gas concentrations. Next question, is this a natural process or is it human caused? The graph A shows that natural temperature drivers like volcanic emissions, solar output, and orbital variances have remained flat over the past 140 years, whereas temperatures have increased sharply. Looking at graph B, human emissions of greenhouse gases, primarily fossil fuel combustion, moderated by the release of particulates like soot, match the observed temperature increases almost exactly. We've actually known the basic science of global warming since the 19th century. The fact that the atmosphere must be letting in light energy and trapping some heat was first recognized by Fourier in 1827. Carbon dioxide's role as a greenhouse gas was discovered by Tyndall in 1861. And the first calculation of the effect of doubling CO2 concentration in the atmosphere was published by Svante Arrhenius in 1896. So this diagram shows the stocks and fluxes of carbon in the land, ocean, underground, and the atmosphere. The numbers represent reservoir mass, also called carbon stocks, in petagrams of carbon. And 1 petagram is equivalent to 1 billion metric tons. And it also shows the annual carbon exchange fluxes, also in petagrams of carbon per year. The black numbers and arrows indicate reservoir mass and exchange fluxes estimated for the time prior to the industrial era, about 1750. The red arrows and numbers indicate the annual fluxes averaged over the 2000 to 2009 time period, the anthropogenic additions. So these fluxes are an alteration of the carbon cycle beginning in the industrial era. The red numbers in the reservoirs denote cumulative changes of anthropogenic carbon over the industrial period. So by convention, a positive cumulative change means that a reservoir has gained carbon since 1750. And the cumulative change of anthropogenic carbon in the terrestrial reservoir is the sum of carbon cumulatively lost to land use change and carbon accumulated in since 1750 in other ecosystems. So if you look at the numbers, the largest storages of carbon are in the oceans, in the intermediate and deep sea, 37,000 petagrams. The other large storages are in vegetation, which is still maybe 2 orders of magnitude smaller than soils. Soils is actually larger. Permafrost, about the same as soils. And then ocean floor sediments and fossil fuel reserves, gas, coal, and oil. There's about, before the industrial era, there was about 589 petagrams of carbon in the atmosphere, and we've added 240 petagrams as of this NOAA graph, which I think is from a few years ago, so it's increased since then. And we're increasing the amount about 4 petagrams of carbon per year, so it's continuing to increase. The amount, so the oceans are continuing to absorb some of this excess carbon. So we, as you see from the fossil fuel reserves, we've burned about 365 petagrams of carbon so far, and there's still a lot left there. If we were to burn all the remaining coal, oil, and gas, where would that carbon go? Some of it's going to go in the ocean and absorbed by vegetation, but a huge amount of it is going to go into the atmosphere. You can see from the fluxes from fossil fuels and cement production, about 7.8 petagrams of carbon per year going into the atmosphere. And then land use change, cutting down forests for agriculture and development, or burning forests or natural forest fires. It adds another about 1.1 petagrams of carbon per year into the atmosphere. So some of that is absorbed by the oceans, some of it is absorbed by vegetation, and a lot of it, 4 petagrams per carbon of carbon per year, stays in the atmosphere, is added to the amount in the atmosphere. One thing to note, that see that block of storage in permafrost, 1,700 petagrams of carbon, that is now being emitted into the atmosphere. Since this graph was made, we're having the permafrost is melting, sometimes in the form of huge explosions in Canada and Siberia, exploding methane, which is a very potent greenhouse gas, into the atmosphere, which is very bad news. So the largest source of carbon, atmospheric carbon, is the burning of fossil fuels, which has gone up dramatically since the Industrial Revolution, especially beginning in the 1950s. You can see how much it's gone up since the 1950s. The energy trapped, human-released greenhouse gases are now trapping as much heat energy every day, as much energy as would be released by 500,000 atomic bombs exploding every day on the Earth, which is an incredible amount of energy. Then the more greenhouse gases in the atmosphere, the higher the temperatures again. If we stop burning fossil fuels and destroying forests, we can limit the increase to 1 to 2 degrees Celsius. Otherwise, it can climb up to 4 to 5 degrees Celsius, which would have devastating consequences. So let's talk about those consequences. Where is this extra heat going? What is it doing? What are its impacts? As you saw from that graph earlier, some of the heat is going into the air, some is going into the oceans, some of it is melting ice, and some is evaporating water. And these different pathways of heat create different effects. As we talked about in the beginning, the most obvious effect is higher temperatures, and this has adverse effects on wildlife and people. Like the pika, for example, which is a cold water, a cold temperature animal. And for people, you can see how dramatic, if we continue on our current course, how dramatic the temperature change could be. And heat waves are becoming more frequent and more extreme, which means the highest temperatures are happening more often, and those heat waves those hottest temperatures are higher, so more heat waves. Winters are also warming, which affects which plants and animals are best suited for a particular area. Animals like moose, wolverines, Arctic foxes, and ptarmigans are adapted to cold weather and may not be able to survive in parts of their current ranges. That's something that I work on for my job, is how animals are going to be displaced and where they're going to go. On the other hand, warm winters benefit pests, weeds, and diseases. Mountain pine beetles have killed almost 30 million acres of pine trees across the American West over the past decade. And one of the reasons for the huge size of this outbreak is that the beetles are benefiting from longer growing seasons and less harsh winters. So more of them, they can breed more often and more cycles, and there are more of them, and it's just destroying the forests in the West and in Canada. So 93% of global warming heat goes into the ocean. And like land temperatures, ocean temperatures are rising. In 2020, so you can see from the graphs that continued to increase. Along the Northeast continental shelf, ocean temperatures rose 3 times faster than the global average. So this regional warming that we're experiencing here in the Baltimore area or the mid-Atlantic up into the Northeast US is accelerating dramatically, with temperatures now rising 1/4 degree Fahrenheit per year. That was between 2007 and 2016. Sea surface temperatures are projected to increase an additional 2.3 to 4.9 degrees Fahrenheit by 2100, depending on the emissions scenario. So that's a huge increase. And data show that the entire water column is being heated, not just the surface. And half of this increase has occurred in less than 20 years. Arctic sea ice has decreased on average between 3.5 and 4.1% per decade since the early 1980s. In September, when ice coverage reaches its annual minimum, the extent has decreased 10.7 to 15.9% per decade. Arctic sea ice loss is expected to continue, very likely resulting in nearly ice-free late summers by the 2040s. Among other effects, the loss of sea ice means no seal hunting habitat for polar bears. So polar bears are in big trouble. They're going to lose their hunting habitat. Glaciers and ice sheets are also melting rapidly, which is creating higher sea levels. I've been to Antarctica and seen some of that, seen glacier retreat, and also seen glacier retreat in dramatic glacier retreat in New Zealand and elsewhere. So this shows how ice melting is accelerating. Seasonally frozen ground is also decreasing. Spring snow cover extent, maximum snow depth, snow water equivalent in the Western US, and extreme snowfall years in the Southern and Western US have all declined. Large snowpack declines are projected for the Western US, which means less water available for river flow, irrigation, and drinking water. In the Western US, people depend a lot on snowfall melt for water, drinking water. And melting land ice and thermal water expansion are raising ocean levels. They've already risen an average of 20 centimeters since 1900. Sea level rise has dramatic effects in flat areas, and it's accelerating. More than 5,000 acres of wetlands have been lost in Blackwater National Wildlife Refuge since the late 1930s, which is a place I worked when I was worked for the state of Maryland and for the Conservation Fund. Annapolis, Maryland, where I live now, and Baltimore, where I used to live, are flooded by normal high tides now. And they both are, Annapolis and Baltimore are some of the most flood prone. They've increased in flooding more than almost any other places in the entire country. Annapolis experienced 63 high tide floods in 2017, compared with about 4 in the early 1960s. Sea level is projected to increase up to 2.4 meters by 2100, or 8 feet. So we are seeing dramatic tipping points in Greenland and Antarctica, with major ice sheets collapsing into the sea. So RCP 2.6, so the scenarios depict what the heat energy level, average heat energy level on the surface is. So 2.6 being the smallest, 8.5 being the largest for modeling purposes. So they're used for modeling. So RCP 2.6 is the scenario where emissions peak before 2020, which they haven't. RCP 4.5 is the one where they peak around 2040. And RCP 8.5 is the one where they keep increasing as usual. In my opinion, we're looking at RCP 4.5 unless we have more climate deniers electing president of major countries, in which case we're in really, really big trouble. But RCP 4.5, which is where I think we're headed, so we're looking at about 1.2 meters of sea level rise on average. And so here's what New York City would look like with 2.5 meters of sea level rise near the top range scenario. And here's what Baltimore could look like on an average day. We would have to take canoes or rafts to get to Balticon. It'll be like Venice. Heavy precipitation events. So they've increased in both intensity and frequency. The largest increases have been in the northeastern US, as we saw with Ellicott City. The frequency and intensity of heavy precipitation events are projected to continue to increase. Yeah, warmer water temperatures and warmer air temperatures mean bigger storms because there's more energy and then there's more water in the atmosphere. And also worse droughts, especially in places like the southwestern US. So the intensity, frequency, and duration of North Atlantic hurricanes, as well as the frequency of the strongest hurricanes, have all increased since the early 1980s. And models project that hurricane intensities and precipitation will further increase as the climate warms. The frequency of the most intense storms is also projected to increase. So this data that I'm showing is all from, most of it is either from the IPCC, International Panel on Climate Change, or the US equivalent, the National Climate Assessment. And I've worked on both of those. Sea level rise is expected to further increase the extent of inland flooding from coastal storms. And this shows flooding in downtown Annapolis from Hurricane Isabel, which also caused quite a bit of flooding in Baltimore and all over the Chesapeake Bay. Many regions of the country are already seeing more of their precipitation being concentrated in the heavier precipitation events, creating potentially severe flooding like that occurred in Ellicott City in 2016 and 2018, which they call the equivalent of a 1,000-year storm, meaning it should only happen on average every 1,000 years. And it happened twice in 2 years. So, and then conversely, we're seeing longer periods of drought in between those strong storms, especially in the southwestern US. So due to higher temperatures, increasing evapotranspiration, droughts have reached record intensity in parts of the US, especially the Southwest. And the Southwest is already in a mega drought. They're in their worst drought in 500 years since the height of the the Hopi and Pueblo civilizations in the Southwest US. People ask, well, why did they die out? Well, it was a mega drought, and we're in a similar mega drought now. And it's predicted to dry even further due to reductions in precipitation and of increased evaporation. The Pacific coast has also experienced severe droughts recently. With increased drought, we're seeing increasingly calamitous fires all over the world. The incidence of large forest fires in the Western US and Alaska has increased since the early 1980s and is projected to further increase as the climate warms, creating profound changes to some ecosystems. And this photo is an actual unaltered photo from the Eagle Creek, Oregon fire. And in my opinion, is the perfect metaphor for how we've been treating climate change in the US. NOAA's Northeast Fisheries Science Center has documented northward or deeper water shifts in nearly 3/4 of species that it has investigated, including important species like lobsters, mackerel, cod, flounder, haddock, and shad. So they are shifting, they're relocating, they're changing where they are. And rising temperatures are leading to changes in fish populations off the coast of Maine, where many puffin parents raise their young. And puffin populations are decreasing dramatically. The chick survival has dropped. Algal blooms are another side effect. They're exacerbated by warmer oceans and large precipitation events, which are very harmful, like red tide, harmful to seabirds, turtles, dolphins, whales, manatees, and fish. Warmer waters also cause coral bleaching. Coral reefs are some of the most biodiverse habitats on the planet, home to nearly 1/4 of all ocean species. I grew up in South Florida, scuba diving. It's long been one of my favorite things to do. And so this really reaches home for me. So what happens is the higher water temperatures cause coral polyps to expel their algae, which helps them produce food. And this coral bleaching can kill the coral and put the health of the whole reef system at risk. So the CO2 taken up by the world's oceans, most of the CO2 dissolves in the seawater. And it takes on, when it dissolves, it takes on a slightly different form. The carbon dioxide combines with water to form carbonic acid. As a result, the oceans have become 30% more acidic than they were prior to the industrial era. And acidity is projected to continue to increase about 0.5% to 1% per year. And so what are the impacts of this? So the hydrogen ions, so pH measures the hydrogen ion concentration. And they attach to carbonate ions and form more bicarbonate, which is important because carbonate, but not bicarbonate, is the key building block for the skeleton of everything in the ocean, from corals to shellfish to many types of plankton, because they combine carbonate with calcium to form calcite or aragonite, that mineral, which they use to form their shells. And these planktons and shellfish are the base of the food webs of the oceans. So it affects coral reefs, plankton, and shellfish. Climate change can also increase the risk of many infectious diseases through increased temperatures, heavier rainfalls, and tropical diseases moving further north. Warming can allow mosquitoes or ticks to expand their habitat ranges and reproduce more frequently. And some viruses also incubate faster inside mosquitoes and other vectors when temperatures are hotter. So this shows projected changes. I'm going to have to zip through some of these slides so I can get through how we can fix these problems. This shows projected changes, impacts, and risks to humans and ecosystems for land-based processes compared to the temperature increase. So we're already seeing water scarcity, soil erosion, vegetation loss, and a lot of other negative effects. The higher the temperature climbs, the more severe the impacts. One thing to note, above 3 degrees Celsius, we will see many vegetated areas turn into deserts. Yeah, these are some of the impacts. So we're already seeing major impacts to coral reefs, and we're going to see continued, as temperatures rise, we're going to see impacts to many other ecosystems also. So this slide shows that, so climate change isn't the only stress on ecosystems and local communities, but it acts as a threat multiplier. So it makes things like clearing forests and land for agriculture or development, which we do, and poaching and overfishing, and invasive species. Climate change makes all these threats worse. And because humans rely on a healthy environment for our existence and well-being, impacts to ecosystems equate to ecosystems to people. The coronavirus pandemic being an example of that, and possibly harbinger of worse things to come. So what can we do about it? There are 2 basic types of responses to climate change. Mitigation means reducing the sources and enhancing the sinks of greenhouse gases to reduce the extent to which climate change happens. And adaptation is reducing the negative impacts of the change that does happen by adjusting natural and human systems to reduce the harm. So remember, the more greenhouse gas we emit into the atmosphere, the higher the temperatures and the greater the disruption of the biosphere. And the policies we choose over the next 10 to 20 years will determine the pathway of our emissions concentrations. If we stop burning fossil fuels and destroying forests, we can limit the increase to 1 to 2 degrees Celsius. Again, we're already at 1 degree Celsius now. We can limit it to, they're trying to limit, the UN is trying to limit it to 1.5 degrees Celsius. 2 degrees is probably more realistic. If we don't do anything, it could climb up to 4 to 5 degrees Celsius, which could have devastating consequences. In fact, recent modeling has shown that various tipping points would likely be surpassed. The melting of permafrost, which is already happening, and possibly the loss of stratocumulus clouds, which could add, if that happens, that could add an additional 8 degrees Celsius of warming, and that would render most of the planet uninhabitable. That's the sort of thing that has caused mass extinction events. So we definitely don't want to go there. We do not want to go to these tipping points scenarios. The good thing is we already have the technology to reduce climate change by replacing fossil fuels with renewable energy and capturing our atmospheric carbon in plants and soils. Most countries have already committed to doing this, including the US now. So we don't have time to go through all these, but Project Drawdown, which I encourage you to take a look at, drawdown.org. identified 80 different solutions to reduce CO2 emissions or remove CO2 from the atmosphere. So first of all, we have to stop burning fossil fuels and destroying forests and wetlands, but no single solution can do the job. We have to consider all of them. And most of these would actually save us money. So look at number one here. The number one thing that we can do, the single most effective thing we can do to reduce climate change is phase out hydrofluorocarbons. So HFCs replaced CFCs, chlorofluorocarbons, and HCFCs as refrigerant chemicals because if you remember, CFCs were destroying the ozone layer in the stratosphere, causing ultraviolet light, increase in ultraviolet light, which causes skin cancer. And we've phased those out. The ozone hole is repairing itself, which shows that we can solve big planetary problems. You know, we can put people on the moon, we can eliminate the ozone hole, we can do other things. We can solve global warming also. There's an accord, a UN accord to phase out HFCs that could avoid a huge increase in CO2, a huge increase in global warming by doing that. Okay, some of the other things, wind turbines, of course, reducing food waste and meat consumption. Those are the number 3 and 4 ways we can reduce greenhouse gas emissions. Then there's population growth and resource consumption. Those are the key drivers of land use change, climate change, and biodiversity loss. There are 4 strategies that can reduce population growth. Educating girls in developing countries, family planning, empowering women in the workplace and society, and although it may seem counterintuitive, reducing infant and child mortality. These are all great things to do, regardless of their effect on the climate. The fact that they also reduce climate change is a bonus. So there are many other solutions to climate change, and most of these have huge side benefits. So we should be doing them anyway. Engineering solutions. So solar radiation management. It's a type of engineering to reduce the amount of solar energy reaching the Earth's surface by reflecting sunlight. So things like deploying space reflectors, atmospheric aerosols and reflectors in deserts and rooftops. One thing to note, these measures are extremely expensive. Painting rooftops and parking lots white would reflect sunlight and also reduce the heat in urban areas. And perhaps better, rooftops and parking lots could be equipped with solar panels, which would convert the sunlight to electricity and also reduce heating from the rooftop. So we have solar panels on our roof, so we get electricity from that, and it also reduces heating during the summer by absorbing that sunlight rather than that sunlight heating up our roof and heating the house. Then there's carbon dioxide removal. Some proposals include fertilizing oceans with iron to create algal blooms that then sink to the seafloor, exposing mantle minerals like olivine, which combine with carbon, injecting CO2 underground, which is done in some oil extraction. So all 3 of these are controversial with potentially problematic side effects. Although injecting CO2 underground at where the oil is extracted is a reasonable thing to do, and it also helps get the oil out of the ground. The enhanced weathering, tearing apart mountains to expose rock to reduce CO2 is a ridiculous idea. Ocean fertilization is perhaps promising, but we don't know what the long-term effects will be. Okay, however, we already have a perfectly engineered device to remove CO2 from the atmosphere. They're called trees. And their biomass and soil. Forests are powerful carbon storehouses. Forest protection prevents deforestation emissions, which are 10 to 15% of global emissions are cutting down trees. And it enables ongoing carbon sequestration. And the most critical of all the forest types is primary or old growth forest. Protecting wetlands and prairies also can reduce CO2 out of the atmosphere and prevent it from being set into the atmosphere. Restoring degraded land can sequester CO2 in plants and soils. And depending on the current condition of the land, there are practices to optimize its carbon storage potential. Biochar, it's a charcoal used as a soil amendment. It's made from wood and other biomass via pyrolysis. And it also has other great benefits like increasing soil fertility of acidic soils, increase in agricultural productivity, increasing water retention, and it reduces pressure on forests by retaining soil fertility. Okay, I don't have much time to talk about climate change adaptation strategies, which is sad because that's what I do for a living. But they include resistance, attempting to keep an ecosystem intact and relatively unchanged, resilience, improving the system's ability to bounce back from a disturbance, and transformation, which is facilitating a system to respond in new ways, like planting species adapted to a hotter climate. Resistance strategies include protecting climate refugia, so areas that don't warm as much. So protect those areas and make sure that they stay cooler. So wildlife that have to move from climate change have a place to move to. And also protecting forests and wetlands help humans by reducing flooding during storms and retaining water during droughts. Resilient strategies help improve a system's ability to bounce back from a disturbance. Things like restoring native vegetation, limiting pollution, controlling the invasive species, reducing hazardous fuels, and transformation strategies. So improving landscape connectivity to allow wildlife and plant range shifts, or adding species that are more heat tolerant or possibly drought tolerant or salt tolerant. Climate adaptation will often employ multiple types of strategies. So what can you do personally? You can do things to reduce your personal climate footprint. Again, go to drawdown.org. Political action, support climate action at the local, state, and federal level. You can work locally to support climate resilience. You can plant butterfly gardens or rain gardens in your yard or elsewhere in your neighborhood, like pollinator habitat, stream restoration, land protection. Get involved with groups that do that sort of thing. Plant trees. So for more information, I will paste this into the chat box, and I'll take any questions. I'll look at the, unfortunately, we ran a little long, for which I apologize. This sort of thing always happens. Let me paste these into the chat. So they include, let's see here, let me find the chat here. Here we go. Oh, there's a whole ton of chat. So don't take my word for it. Look for yourself. I've posted some reputable sources of climate science. You can take a look for yourself. And then again, Project Drawdown is one of the most comprehensive compilations of solutions. So that's drawdown.org, drawdown.org. Post that in, put that in here. All right, so you can grab those. So I will be available on the Discord, to answer questions. I'm not sure how much time we have. I'll rely on our host. So how do we know that ice temperature data is accurate? So measuring any type of data, you calibrate it against other sources of data, temperature from the ice core samples. So compare that to other data like tree cores and things like that, and known temperature records. So the ice, that's measuring CO2 levels. So that's not measuring temperature. That's measuring CO2 levels, and that you just you stick in a meter and measure the CO2. So that's pretty straightforward. Large temperature swings. There's a bunch of things here. What are the chances of wet bulb atmosphere event happening? So for the whole atmosphere, that's if we don't do anything about, if we don't reduce our impact on the climate, and we have a bunch of feedback mechanisms